Good morning, here yet again for another lovely session of CENG 3325 Structural Analysis. Today we're going to be looking at the method of virtual work for frames. This is going to be the 20th lecture in the video series, and today again we're continuing on our work with virtual work. And previously we've looked at virtual work for both trusses and for beams, and now for our final segment on virtual work we're going to combine it all together and look at virtual work for frames. So, virtual work for frames. So let us review the principle of virtual work. So let us review briefly the principle of virtual work. As we have seen already for both trusses and beams, the same principle is involved with both of these. Essentially that the virtual work internal is equal to the virtual work external, although usually I'll actually write it the other way. Virtual work external is equal to virtual work internal. So if you have a virtual unit force, the external work done by that is equal to the internal work done by it. Or another way to state this is the unit virtual load times the real displacement is equal to the virtual internal force times the real internal deformation. The real internal deformation. And this is our fundamental principle of virtual work. So I want to review through this for both trusses and beams. Look at the forms of these for both trusses and beams. So for trusses, when this is applied to trusses, we'll have the following equation. So again, we're using the same general form for both trusses and beams, but there are slightly different variations. So for trusses, let's get that, and beams. For trusses, our form, this equation then takes the form 1 times delta is equal to the summation of FVI, the virtual internal forces, times the real internal deformations, or lowercase delta, or 1 times delta, an expression for the deformation or the elongation, is then we just have the same FVI, but our internal deformation, or our real deformation, or our member elongation, is F internal, the real internal force, times the member length divided by AE. Again, we have seen this before. This is just a bit of a review. And then for beams, we have 1 times delta equals, well, there's two forms for beams. 1 times delta is equal to the integral of, from 0 to L, along the length of the beam, of MVM divided by EI dx. And we also, if this is what we use if we want the displacement at a point, and if we want the rotation at a point, we use the equation 1 times theta. We're here we are applying a unit couple instead of a unit load, and this would be equal to the same integral from 0 to L of mv, our virtual moment, times our real moment function divided by EI, and of course integrated dx. And in summary for these, when do we use each of these? By themselves anyway. Trusses, again, going back to statics even, trusses are elements where you have pure axial load. Axial force in members. So this form of energy balance is valid when you have only axial force in members. And this kind of energy balance is where you have pure bending, only shear in moments. So this is our beam equations here are valid when you have no axial force, only shear in moment. Only shear in moment. But again, hopefully that is just a review. So,
Can I ask a question?
yes.
I didn't ask this last class, but how can they be the same equation for slope and deflection?
The
I don't understand that.
Okay, the question is, how can these be the same for both slope and deflection, the right-hand side of here? Well, basically, how can that be both the same? Well, ultimately, what does this all come to? What unit would this all come to here? The right-hand side of the equations. What unit does that come to?
The right-hand side?
Yep.
It's going to be inches or feet?
The actual final unit is going to be in energy. This is the method of virtual work. And so whether that, so we have this internal work, the internal work that comes from bending. And so the internal work that's produced by bending, again, the right-hand side is the internal work, and that's caused by bending. And what ultimately is causing that bending, whether it's a point load or a couple, doesn't actually matter to the expression for the internal energy. So what you'll do, so now you won't get the exact same functions. Like if you have a couple versus a point load applied, you'll end up finding different moment functions. But the actual expression for once you have those moment functions, you handle them in essentially the same way. Does that make sense?
Yeah.
Okay. So now let's combine all this together and generalize. So we have something where we can look at elements or members that have only axial force. We have something that we can look at members that have only bending. Now I want to combine them together. So let's combine the, let's generalize this. So let's generalize our virtual work expressions. So instead of looking at just beams and trusses, I'm going to take those equations and generalize them into two broader forms. So let's say we have the work, the internal virtual work done due to axial forces. Due to axial forces, member axial forces. And instead of saying just 1 times delta or whatnot, for now, I'm going to give this a label of W VIA. VIA. This is work virtual internal axial. And this is equal to the summation of the force virtual internal times the real force Fi L over AE. And again, and here one thing we are assuming is constant cross-section. Constant cross-section is assumed in this. And then let's look at the virtual internal work or internal virtual work done due to bending of members, due to bending or flexure of members, and I'm going to say that WVIB. This is the work due to bending, the internal virtual work due to bending, and it's going to be just like the previous one for beams, except now I'm going to add a sigma to the integral. So previously you had the same integral, but now I'm going to have a sigma here, and it's going to be MVM divided by EI dx. EI dx. And the sigma we are summing up across individual members, summing up the work on each member in a frame. The work to deform each member in a frame. So hopefully this is kind of already hopefully congealing in your head, or hopefully you can already kind of see where this is going. So this is summing up the work done to deform each member, or done to the work done to bend each member. To bend each member. So if I combine together, then the total virtual work, or virtual internal work, well, WVI will be equal to the sum. So again, because this is energy, because we're dealing with energy methods, one of the really nice things about energy methods is you can simply add them together. Whether a deformation is, again, at the end of the day, if you're applying energy to something, energy is a scalar quantity rather than a vector, so we can simply add together the energy terms. That's the really nice thing about energy methods. So it's equal to, so the final virtual work term, or the internal virtual work term, is just the summation of each of these things. So the summation of FVI times FIL over AE. Basically, this is the work done in an axial deformation, and plus the summation of the integrals of 0 to L of MVM over EI dx. Again, maybe I'll just annotate this. This is the work to internal virtual work, virtual work to stretch the members, like axially stretching, deforming. To stretch the members in a frame. And this would be the internal virtual work to bend the members. So now we can see that working with frames really isn't so difficult. All we're doing is combining together the previous expressions we already used for both trusses and beams. But let me put this into a final form. I want to tack on or I want to recombine this with the external virtual work forms to produce our final equations for frames. So final virtual work expressions. Or final total virtual work expressions. And that is, again, once we combine, once we say work virtual external is equal to work virtual internal, we can just combine these together. And for deflection, for the deflection case, we'll have this equation. For deflection, we have 1 times delta is equal to the summation of FVI times FIL over AE plus the summation of the integral from 0 to L of MVM over AE dx. And then for for rotation, so this is what you use if you want to know the deflection of a frame at a particular location. And then for rotation, if you want to know the slope of the beam, well, 1 times theta is equal to the same virtual work, internal work expression. So 1 times theta is equal to the summation of FVI times FIL, you're probably getting really tired of writing this, over AE, plus the summation of the integrals from 0 to L of MVM over AE dx. So, and these are our long form, unsimplified virtual work expressions for frames. However, I will add another note to this, and that is that often we can simplify these one step further. But you won't always be able to do this. It depends on the exact proportions of your loads. So, but I will note this. You often can simplify. And the reason for this is, in most cases, outside of trusses, in most cases, cases with common engineering materials and loads, engineering materials and loads the work from axial forces or the work from axial deformation is much less, much less than the work from bending. Is much less than the work from bending. Than the work from bending. So often we can neglect the axial terms here. And often for deflection, we can just say, again, 1 times delta is equal to the summation of the integral from 0 to L of mv m over AE. Oh, sorry, that should not, wow, that is a really bad typo. Derp. Sorry about that. I got stuck in a habit of AE. That should be EI. Sorry about that. Let me make sure I didn't do that on the previous slides. Nope, just a typo there. Sorry about that. Yes, Scrivener's error. Bartleby, the Scrivener. Anyway. EI dx and 1 times theta is equal to the summation of the integrals 0 to L of the same thing, basically, mvm over EI dx. And in most cases, you're going to be able to get away with just using these and not having to worry about the axial work terms. Okay, so we have our equations, but I would like to go... Huh? Question?
Yeah, on the same, right?
Yes, these are the same, yes. Just like in the previous cases. So we have our equations now, but I would like to go through a general list of steps, to analyze. So I would like to look at the procedure for analysis. Any questions on this so far? So let's see. Again.
No, just leave the page up there for a minute, so write it down.
Just a second. Let's see. Okay. So again, these are general equations, but I do think we need to move on. So I do want to get to a procedure for analysis. So the first step is going to be to analyze the real system. Analyze the real system. So when we analyze the real system, what is this going to mean? Well, we will, you need to draw the exploded view of the frame. Find the member end forces and step 3 for this, under analyze the real system, calculate m as a function of x for each member. So the tricky thing about this is you're going to be doing this m as a function of x for each member in your frame. Two, I want to analyze the virtual system. I want to analyze the virtual system. And again, and we're going to use the same kind of procedure we did for beams. If deflection is desired, we will apply a unit load in the direction of assumed deflection. In direction of assumed deflection, at the location deflection is desired. At location deflection where deflection is desired. So really no different than what we've been doing for beams and trusses. And if slope is desired, we will apply a unit couple. At location, slope is wanted. So really, this is the exact same thing we've been doing previously with beams and couples, or sorry, beams and trusses. At location, slope is desired. And then you'll draw the exploded view for virtual system. And then finally find mv as a function of x. The virtual moment as a function of x for each member in the frame. For each member in the frame. Again, this is our first two steps. This is just completely analyzing the real system and completely analyzing the virtual system. So you're going to put the real loads on the structure, and then using methods of statics that we've looked at previously. Remember way back when a couple of weeks back, or maybe a month or two ago, when we were looking at finding shear and bending moment diagrams for frames? That's what you're doing here, except now we're just taking it a step further, and well, we're actually doing it twice for each frame just to find one point of deflection. But it can be a bit tedious, but that's okay, relatively. So then let's move on to step 3. Step 3 is going to be to resolve the zones of integration. So just like we did for beams, we're going to have to often resolve zones of integration. Resolve zones of integration. So again, as we remember from beams, m of x and mv of x are piecewise functions. M of x and mv of x are piecewise functions. So what you may need to do is, you need to make sure that on any beam that you're integrating, that the bounds of your piecewise functions match up with each other. Again, this is the exact same thing we've had to do with beams, integrating for beams. So again, here, break any zones apart if needed. Break zones apart if needed. Until mv of x and that's a v of x there, and m of x have same bounds. Bounds of integration. And if you're having trouble recalling how to do that, feel free to take a look at the videos on finding moment functions, applying virtual work to just simple beams. Also, a key thing to keep in mind, just like we did with beams, you must keep the origin constant. Keep origin and the positive x direction constant on a given member. In other words, if you have a frame, something like this, if in your, let's say this is your real system, something like, maybe this is your 10 kip, maybe you have a 10 kip and a 12 kip or something, and this is your real system, this is your real, and then maybe your virtual system, maybe you're interested in the horizontal deflection here. Keep origin, that should say and, plus x direction constant on a given member. So if you have a virtual system here, and maybe we wanted to find the deflection at the upper left-hand joint there, so I'd have a 1 kip load there. But if I wanted to know, if I wanted to integrate each of these, I would want to use the same plus x direction, same origin for each member. So, in other words, on this element here, if I call this x equals 0 and going down positive, I would have x positive like this. But if I did that, I would want to make sure to do the same thing here. If I call the left end here positive, left end here positive, I must use the same thing. Or the left hand here 0, so this would be 0 here as well, and then positive to the right, same thing here. Again, there is no hard and fast rule about which end of the beam or column is your 0 end, but the key thing is that you have to be internally consistent. 0, x positive. Like so. So any questions on this? Okay, hopefully fairly straightforward. And then finally, step 4. Step 4 will be to apply your virtual work equations. Depending on whether whether you're looking for slope or deflection, you'll simply choose the appropriate one. Oh, sorry about that. You'll apply the appropriate virtual work equation. Either 1 times delta equals the summation of the integral from 0 to L of mvm over ei dx, or 1 times theta is equal to the summation of the integral 0 to L of mvm over ei dx. And this is our basic method for virtual work. So we have this, and I will work through an example. So I do have a few other notes on this though. Follow-up notes. Notes. If deformation for axial load is large, remember, we assumed previously that we said that in most cases the work done by axial deformation is minimal compared to the work done by bending. But if deformation from axial load is large, relative to bending deformation, to moment deformation, then axial loads cannot be neglected. So in that case, you'd have to go back to the full expression, which would be 1 times delta equals the summation of FVI times FI L over AE plus the summation of the integral from 0 to L of MV M over EI dx.
So, like that example that you had comparing the origins, like keep them constant, that's an example where you would take in actual force, right? So that's the 12 kips.
I wouldn't necessarily say even that case. No, that wouldn't necessarily be a case where the deformation was large. Really, you just have to look at, okay, the question is, how do you know? Well, it's somewhat of a judgment call. What you might look at is you might look at the, well, one way to do it, you might look at the stress from bending versus the stress from axial force. So if you found that your members had a maximum bending stress of, 2 KSI and a maximum axial stress of, 10 KSI, well, in that case, a stress from axial load of 10 KSI, well, in that case, that's a system that's actually dominated by axial load. And so it really just depends on what type of system you have. But for most general frames, even frames like I drew previously, that one with the 12 kip load and such on it, in most of those, the work done by bending is going to be much greater than the work done by axial load.
So like when we analyze the real system, we look at the actual force and we look at the bending moment?
Yes,
Rather than be
exactly.
like, okay, that's where we don't need to use actual force.
Yes, exactly. And when in doubt, you can always just do both of them and take a look at them and see if you can neglect it. And so there's that. And one thing you could do there is you could just, it's basically the same basic idea. Now let me generalize these steps a bit more. Or more generally, I'm going to give this as a bit more simplified description for the whole method. Again, analyze frame for real loads. We're going to analyze the frame for real loads and find internal forces due to real loads. And in particular, m as a function of x. 2, we'll analyze the frame for the virtual unit load. So I'm just restating what I've looked at previously, but in a more general, concise form. Analyze frame for for virtual loads, or for virtual load. Again, placing the virtual load at the location where deflection or rotation is desired, and calculate the virtual moment as a function of x for each member. And then 3, finally, balance. We are going to balance the work virtual external equals the work virtual internal according to the previous equations. According to the previous equations. And some final notes on key items, just common prats and pitfalls again. 1, as mentioned, keep origin constant. And direction of integration constant, at least across individual members. The direction won't have to be lined up between members, but within, say, column A, B, it must be the same whether you're doing it virtual or real. Keep origin and direction of positive axis constant. Constant here. 2, as always with these, what is a common way people usually screw up on this? Units, yes, watch your units. In fact, I suggest when doing this that you just immediately put if you're doing this in, say, if you're using English units, I suggest that the first thing you do right off the bat when you start working with a problem is just immediately convert your length to inches. So if you have your cross-sectional area in inches squared and your modulus elasticity inches to the fourth power, and your modulus of elasticity in inches in KSI, and your moment of inertia in inches to the fourth power, the only thing on your frame that is not likely to be in inches already at the start is your length. So I would just recommend just right off the bat converting your length to inches and just running through the whole problem with inches, and then you don't have to worry about any unit issues. So we have that, and 3, use compatible zones of integration. Zones of integration, and again, as we've discussed previously, then for the negative, if you get a negative, I'll just say if you get a negative value, and this is especially not popular, but possible with frames because they can often deform in ways that are less intuitive. Negative final value for deflection. What does that mean?
It's opposite of your assumption.
Exactly. It is the real deflection. That just means the deflection. Then the deflection is opposite the direction you assumed. Direction you assumed. And then finally 5, watch for discontinuities along frame x-axis. Or I should just say along beams/columns. Question?
No, just, it said watch for discontinuities, but your 5 was off on the other list.
Oh, yeah, it's kind of off of it. Yeah, that is, I guess that is kind of funny. Hey, that is appropriate. Yeah, it says watch for discontinuities, and there's discontinuity right here. Well, this thing on here wants to grab the text, but, huh? No, I'm not going to fix it. I'm just going to let you watch out for it. But no, so you're watching for discontinuities. What that means is you're watching for other loads coming in. You're watching for changes in cross-sectional area. You're watching for connection points, whatever it might be. Anytime there's discontinuity in your beam or your column, you're going to need a new boundary of integration there. All right, so that is the general method for solving, for applying virtual work. The method of virtual work to frames. That'll do it for today. Thank you for watching, and as always, thank you. And of course, actually I should finish up. We will go, I will put together later a video with a long form example showing how to do all this. But again, that'll do it for today. Thank you for watching, and as always, thank you.